Thank you, everyone, for joining. This is going to be a really good session. I'm really happy to have you join. I know that some folks are streaming in. We're just at the top of the hour here, and we will have some more people coming in as they wrap up the previous session. But for this one, I'm really excited to have everybody join. If it's your first time joining the TMLS events, you'll see that we do a day of workshops, actually two in this case. And then tonight, you're actually going to receive an email with a unique code to join the Hopin platform, which is where we host the conference portion. That is the breakouts and the keynotes taking place on the 17th and 18th. So look out for that email. Also, if you haven't already joined the Whova app, that's the event app. It's really a good way to meet some of the other folks that have attended the event, that are working in the data science fields, learn a little bit more about their projects, and also see some open positions that are out there in the community as well. You can post positions, message people, join them on one-to-one, or request chats, and so on. If you have any questions, you can also post questions there or on our website, torontomachineLearning.com, where we have the chat feature as well. So I hope it's been more or less a good experience so far on the first day. This is the last session slot for our workshops on day one. But I'm really excited for this one because in this talk workshop, it's really designed for ML practitioners, specifically those who are interested in maintaining ML pipelines in production. So it's, as Shreya had mentioned, not going to be discussing model development, data analysis, or feature engineering techniques, but we will learn about the types of bugs that occur in production pipelines, how to incorporate testing into your ML application code base in a sustainable way, and how to enable on-call ML engineers or data scientists to debug broken pipelines with ML-specific logging, monitoring, and querying. So Shreya has been fantastic. She's not only spoken this first time, this is actually her second time working and sharing back and giving back with the community. So we're very grateful. She's somebody that I'm convinced will be too busy for us very shortly. She's doing great things, and I only see many, many great things ahead. So let me first start by welcoming Shreya, and I'm going to just give you a quick intro for those who have not had any introduction to her in the past. So Shreya Shankar is a computer scientist living in the Bay Area and building systems to operationalize machine learning workflows. Her research focuses on end-to-end observability for ML systems, particularly in the context of heterogeneous stacks of tools. Currently, she is taking her Ph.D. in the RISE lab at UC Berkeley. Some really incredible people coming out of that program, by the way, and in that group. Previously, she was the first ML engineer at Viaduct, did research at Google Brain, and obtained her Bachelor of Science and MS in Computer Science from Stanford. So with that being said, Shreya, thank you so much for joining. I really appreciate it. I will pass this over to you. And for those folks who have any questions, please feel free to post them in the chat here, and I'm sure Shreya can get towards those. Yeah, and I'll let you take it away, Shreya. Thank you so much.
Cool, thanks for the intro. I'm super excited to be here, and hopefully it won't be super boring. I know it's the end of the day for a lot of people, so please feel free to interrupt at any given point if you have any questions. Without further ado, let's get started. So today we'll be talking about a bunch of things. First, I'll start off by giving a little bit of a background on myself and kind of my own interests in this space. Talk about how maybe an ML pipeline might be developed at some sort of organization, which many of you may have a bunch of familiarity with. I'll make the case for observability in ML systems, which again is another big buzzword I feel like that's come up in the past month. But today's main focus will be rethinking kind of how do we apply CI principles to ML pipelines. And I'll do a pretty in-depth demo or tutorial on building and debugging a pipeline, and then a kind of open source project that I have to get some sort of end-to-end tracing and then inject testing at runtime in components of pipelines. And then I'll also talk some more about future work that we at the lab are working on, and would love to get anybody's thoughts on kind of the directions that we're going in, or if you're really interested in kind of trying out these kinds of stuff. Cool. So a little bit about myself. I grew up in Texas, and I moved out to the Bay Area. Gosh, I don't even remember how many years ago at this point. But I moved out here to do my undergrad and master's in computer science, which was a lot of fun. And while I was there, I also did some deep learning research, and I got to do this in the time where people started caring a lot about adversarial examples and quote unquote robustness. And this was super compelling and interesting to me. And I thought, okay, like I'm going to go out into the world and I'm going to join a startup where we do applied machine learning, and all of my handy dandy robustness research experience will come into play. But that was not the case. I did a lot of other things that I never thought I would be doing. I ended up working with volumes of time series data that I never imagined would have existed. And then I also learned a lot about engineering. I think my main job was kind of a software engineer, building infrastructure for data scientists to do like large scale ML and data analytics. And in the time I was there, I was the first ML engineer. And by the time I left, we had several production grade ML services running. And there was a lot that happened, I think, in those years. And that kind of motivated what I work on now. And like hinting, right, in undergrad and in school days, I trained a lot of models. I trained a lot of ML models, and I cared about, I don't know, like how can we be fair, or how can we generalize to unknown distributions, specifically in the case of like deep neural networks. But this was not the case when I went to industry, because nobody cares how many models you've trained. All that matters is whenever you're using those models for inference, they're performing well. And the idea is to try to reduce costs as much as possible, per se, or I don't know. You want to train a few models, but do lots and lots of inference with those models, which really begs the question, right? Like, let's say I've trained models and I've validated it in this offline manner on my own test set. What happens beyond the test set when I deploy it? And how do I, when I see a bug or when I think there might be a bug in production, how do I very quickly react to it, like isolate where the bug is and then like respond? And this is really, really hard of a problem, as many of you are probably very familiar with. Most data science projects, and I'll use that pretty liberally because I took it from a Verge article. I think they were like 87% of data science projects don't make it to production. Not all of them were intended to make it to production, but a good number of them, right? Like, people want to put data science or like some ML workflow in production and just can't. And maybe this is for a lot of reasons. Maybe like data is not clean and balanced, right? Like canonical data sets that we might work with in the academic world, like ImageNet, or even more recent benchmarks that have come out. Data in the real world is quote unquote always changing. A lot of it is tabular, a lot of it is streaming. It's not really conducive to the kinds of ML workflows and environments that we've studied in an academic context. And last but not least, right, like things are always breaking in prod. And this is not specific to ML. This is like in software, when you're a software engineer, things are always breaking. And we need ops in a way, like there's no way we're going to be able to anticipate all the problems that happen for an ML service in an offline fashion, and then like just expect to set and forget as we deploy it out to the real world. So now I'll jump in a little bit into kind of what it might look like, at least what it looked like for me and several people that I've talked to or worked with, to build an ML pipeline. And I've not really been like a serious ML engineer at like a FANG company or I guess FANG company. But I've also been told that it's similar there. But there's a lot of stuff involved and a lot of people involved in kind of developing ML pipelines. Usually it starts off with some sort of like business planning. Maybe there's some planning meeting or OKR meeting. And somebody says like, we need to, I don't know, incorporate ML into the service or like make some sort of endpoint or API that serve some predictions, whether that be like embeddings to use internally, or whether that mean like actual predicted values to showcase to like a customer on an app. Usually some task is defined, and some data scientist or like team of data people are like, okay, we'll get started. And even at mature companies, apparently it's not always the case that all like the evaluation metrics are well defined in the beginning. How people are going to act on the model outputs are well defined, or like what acceptable quote unquote errors are. There's like a lot of work in research around like model cards, for example, like intended use of a model. Or like I recently read a paper on like DAG cards that's going to be presented at NeurIPS 2021. this year. It's interesting, I don't know, ideas of how to collaborate on kind of specifying the pipeline's intent. But it's not there. And kind of like the ambiguity in this lends itself to some sort of like bespoke process that goes on in a data science team. Like it's some sort of like, I like to call it garbage in, magic out, because I think that this was like my entire ML job when I was doing ML, like get some data, doing some EDA, identifying, okay, what is the prediction task and the evaluation metric, and then train and evaluate some models. And then maybe this is like where I use some like experiment tracking framework to kind of isolate like or aggregate kind of like all the experiments that I'm running, and figure out what's the best model or the best architecture, like the best depth for my random forest or my GBDT that I'm going to deploy on this task. And then I say, okay, I want to deploy this model. And then this is where, right, like at least the first time or the first few times that I deployed ML models, I thought, okay, like I'll just wrap this in a DAG and kind of, I don't know, serve predictions, maybe schedule it. If it's trying to run real time, like I'll do that. I don't know, I'll build some endpoint. But then I didn't quite plan out what I was going to do after I deployed this. As if like maybe the traditional software kind of monitoring and observability tools, I think like, okay, like I'll just look at like our mean request, I don't know, request latency over the last 15 minutes. And like, that'll be good enough to know like whether this production service is going well. But this is not how production software works, right? If we want to like deploy something, we need to plan ahead of time what we want to monitor, how we want to like react to failures when they happen. And as a result, I think like production ML is just like a huge nightmare for anybody who's on call, for a whole host of reasons. I'm sure people have faced any subset of this and much, much more. Some of the most recent problems that have come to mind for me are like upstream data that's owned by somebody else, is corrupted in some way or is changed in some way and I wasn't aware. Maybe the model needs to be retrained, but some model developer is on leave or they've left the company and then nobody else kind of knows how this like bespoke ML process works. Maybe the feature generation code has a bug, which is like, I've made mistakes in like feature generation code all the time. Like maybe accidentally like some data is missing and I'm like joining on a column with a bunch of null values. Maybe there's some assumptions that I've made at training time that don't quite hold at the live inference time, right? For example, maybe data has arrived in my system, like, or the labels have arrived after some sort of lag. So maybe that's throwing off some of my estimates for how well I think the model should be doing. And more. You can come up with your own. I think there's a lot that could be going on. Yes, I will post the slides somewhere. Sorry, I'm reading the chat. Please ask your questions. Or maybe the organizers will, I'm not sure. Actually, I haven't sent my slides to anyone. So yes, I will post the slides somewhere. We'll figure it out. Anyways, okay, where was I? Yeah, prod ML, big nightmare. And a lot of this is just, it's so, how do I say this? It's so tedious to just think about what it means to go about like trying to debug something that could happen in like a production ML pipeline. And a lot of this is because production ML pipelines could be like pretty complex in two axes. Like one is like the number of components in a production pipeline. Like as you can see in this diagram here, a pretty simple prediction task with like one model, let's say to like predict, I don't know, or recommend some like movies for you to watch. I don't know, whatever ML test you want to use here, right? Like there's probably some offline process for training and developing the model and evaluating it offline. And then there's some online process for kind of doing this inference in real time. And there's like kind of two separate feature, I don't want to say feature stores, but maybe feature tables or two separate places where features are stored. Maybe artifacts are being shared throughout the online and offline pipeline. And then for each of these components also, like the other axis is like the number of tools you could use to kind of like write the code and kind of solve metadata management problems around each of these components is also massive, right? Like, for example, I want to do ETL, like I could write my ETL pipelines in Spark and schedule them in Airflow, or I could use Argo, or it could be like BigQuery queries because like the data is in some cloud, like G Cloud or whatever bucket. Or maybe I'm using SQL Server, I don't know. Maybe I'm using like different types of tools to store my features. Like I'm pretty sure 95% of people can just like get away with using like a Postgres feature store or feature table. But maybe you'll want to use like a Delta Lake or some sort of incremental ingestion data format. Maybe you're doing your training and evaluation and like, or maybe you have different data scientists in your organization. Like some of them are using scikit-learn, some of them are using TensorFlow. Some of them are using Spark, XGBoost. I don't know. Maybe I can explain, or I can list what, like 100 more tools. But having such a complex stack, right? And like expecting one person, or it's expecting every person to know everything that's going on, such that when something fails, when you're on call, and that person can debug it. That's just like insane to expect. Like the tool blow up, the component blow up is massive. So that's what makes it hard, I think, to actually think about what does it mean to have observability for these kinds of ML pipelines. And because of this, right, life as an engineer, ML engineer at least, is like fighting a bunch of fires or like surviving a bunch of thunderstorms, whatever analogy you want to use, right? You're chasing bugs that could pretty much lie anywhere across the end-to-end pipeline. You're managing all this like amount of metadata around keeping models in production. So like feature stores, model registries, data quality tests, monitoring, whatever you want to put in there. Maybe you're stitching together like so many tools to make your life easier. But like every time you add a new tool, right, like the sustainability or like how easy it is to maintain it, or the maintenance for your pipeline, right, it becomes much harder. But when you think about it, these problems are not like super new, right, to software engineering. These problems are there, and we've seen them before. And SREs themselves have like figure out like how can we survive these thunderstorms. They are also chasing bugs that could lie anywhere across the software service. They're also managing metadata, logging, monitoring metrics, and tracing across software in production. And they're also stitching together crazy amounts of tools to make their lives easier. So if they can do it, right, like what can we learn from all the problems that like DevOps people and SRE people have already faced? And how can we bring the principles that they've kind of figured out? How can we bring them to sustaining ML pipelines? So that's where I make the case for ML observability. And I'll define it pretty loosely as like end-to-end visibility across a given pipeline or system. And why do we need it? Well, I mentioned this before, systems in prod are always going to have bugs at some point. You're just never going to have a bug-free production system, especially as it's evolving over time. And the goal is, right, not to like minimize the number of bugs that ever first show up, or maybe that's like part of the goal. But we also want to minimize like downtime. So that's when we know there is a bug, how can we quickly isolate it and then quickly respond to it? And to achieve this goal, right, when you think about like this from a building the tooling for ML observability, from the tool builder's perspective, right, we want to be able to help engineers identify bugs pretty quickly. And then once they know where the bugs are, we want them to react to the bugs, which is like maybe figure out like, oh, my model is stale, let me retrain it. Or it's like, the problem is like one of the sensors that are producing data are broken, let's go fix that sensor. And let's try to minimize downtime in this whole process. And then we can ask ourselves a question like, okay, this makes a lot of sense. So why don't we just use existing DevOps tools to kind of to solve these problems? And DevOps kind of offers a bunch of tools. And maybe one question to ask is like, why don't we use like CI that we all know and love dearly, right? Why don't we use that? Those tools that run, like, for example, on pull request or like committing to master. So this works for like traditional software systems that change when your code change, or the behavior of these systems change when code changes. But when you think about ML pipelines or even data pipelines more broadly, these pipeline behaviors change on both code and data change. So no longer is it sufficient to kind of like write your GitHub Actions tests, or write your GitHub Actions to run tests upon pull requests, but also anytime like any component in your pipeline is seeing new data, like you can imagine like in some sort of data flow manner, we also need to be able to run some tests and like verify some sort of assumptions that we've had are still holding. And then why not use like traditional monitoring systems or CD tools? That works great when you're trying to look at a few metrics or pretty like simple aggregations, things like mean latency for this endpoint. But a lot of the time, actually, this is a pretty unsolved problem anyways in ML monitoring, but what do you monitor, right? Like these like ML SLAs, like very few organizations are saying like, hey, like I'm posting this like SLA on the service, I'm guaranteeing you some like 95% recall, or something like that, right? Like that kind of agreement with a business team is not well defined. And because of that, or that kind of also spreads out into people are just monitoring almost absolutely everything, like any possible feature, any possible aggregation over a feature, any output, any possible aggregation over an output. And you also might not have, right, like real-time feedback if you want to be computing these kinds of metrics. Like for example, when you do get lag in your labels, right, how can you approximate like what is the performance of your pipeline at any time? So that kind of motivates when we need some new ways of framing, like bringing observability to ML. And a few more differences that we have in the ML ecosystem are that one, we need to like support a wide variety of skill sets. So we're needing to support software engineers, data scientists, data engineers, product managers, biz dev people, truly so many more people. And then also, we might need to rethink like what sort of metadata do we need to log? What metrics do we need to monitor? And then how do we store, aggregate all this information and make it available to practitioners to be able to query at anytime they need to debug a system. So I'll talk a little bit about what I'm working on in my PhD. So let me close my door. Yeah, I'll talk about what I'm working on in my PhD called mltrace. I'm pretty excited about it. It's still very, very nascent, but I'll introduce it. So our goal here kind of is to have this like lightweight end-to-end framework that's centered around execution of individual components in pipelines. And we really want to support like whatever tech stack, whatever, I don't know, combination of tools you may have. How can we, in like a very minimally invasive way, like offer you some sort of like bolt-on observability or like some like bolt-on monitoring? It's open source, so you can set it up and run it in-house. I never want to be in the business of looking at people's data. And eventually, we want to be able to support automatic logging, which we're making pretty big gains towards. I have this like dream that we can build like a React-like library for building ML pipelines where you can kind of chain components together and kind of get like the tests and the metrics to monitor off the shelf. And maybe you just write like the individual component code. Maybe like that's the individual code for training or in the code for training a model. And that's kind of wrapped around like all of these like, I don't know, library specific pluggable components that we have. And then of course we are actively thinking about what does it mean to have a querying framework for users to debug pipelines? How do we like materialize large amounts of information for people to use at debugging time? And the way that we're doing this architecture-wise, several different layers. The topmost layer is the UI layer. So that's both utility functions to be able to log data For example, like inputs, outputs, or test results at runtime. And like, of course, like versions of that data will be stored somewhere. And then of course, like a UI and CLI to be able to query these logs or figure out what's going on. Then there's the execution layer that we have, which basically takes like user-defined components and then runs, like if you're familiar with databases, like runs triggers before and after components are run to both like do testing and to figure out which metric, or also to monitor metrics. And then it commits logs to the database or storage layer, houses all the logs, inputs, outputs, metrics, test results, whatever underlying artifact is being used in your pipeline. And the ways that clients kind of have to work on or work with mltrace, hopefully I'm also thinking about ways to better abstract this. But there are a couple, there's three. One is a component, which is like a stage of a pipeline, very similar to like a Kubeflow component. So for example, maybe that's like model training, or maybe that's like windowed feature generation. The idea is like one person owns a component sort of thing, like at my previous company, some people owned like some of the features that came out of dimension tables. Some people owned features that came out of like aggregations of fact tables. You're using star schema. And then they're also represented by like a name, owner, description, and then some like tags, I don't know. We also have a component run abstraction, which is basically all the logs or the metadata that comes from a run of a single component. And that kind of can include like start and end timestamps, inputs and outputs, like data frames, and then like other metadata like the git commit, or like link to your MLflow experiment or whatever. And then the last abstraction really is a test, or I like to think of it as some sort of reusable computation to perform before and after components are run. And maybe test is not a great term. I'll change that. But this is also like the way that we'll do monitoring of like metrics. You can also do it asynchronously. They don't have to include like assert statements in here. And it'll hopefully make more sense when I walk through the kind of tutorial. Tests are added to components. So basically when you define a component, you say like, this is the name of the component, and this is the owner, description, here's the function, that's the component, and then here are some tests to run before this component is run, and here are some tests to run after the component is run. So we'll walk through a little bit of a demo here. And I think you should be able to follow along if you're like super motivated and interested. Otherwise, you can just, I don't know, watch whatever I'm doing. And the goal here is to showcase the kind of testing functionality that or the prototype that we have going on. There's a lot of room for improvement, but it's more of like, what is the interface for how can we like do good testing in ML pipelines? And what we'll do for the part of this demo, first we'll have ML training and inference pipelines. I wrote them in Python with like really standard Python data science libraries. You can probably use whatever you want. Then after we run these, we're going to run these pipelines, and then we're going to experience some sort of performance drop when the inference pipeline runs for a long period of time. And that will be unfortunate. And so what we'll want to do is figure out kind of what can we do to inspect what's going on in these pipelines. We want to instrument pipelines with mltrace components, and then think about tests to execute as triggers before and after the components are run. So I've kind of written all the code for it anyways, but there's definitely extensions to do. So if you want to follow along, I have some setup instructions here. The prerequisites are like some Python 3.7, at least some Unix-based shell. So if you're using a Windows machine, please use like the WSL environment, and then Docker. There's an mltrace demo repository and the mltrace repository, which I'll post links in the chat. So here is the demo repository. that's not what we want. And then here is the mltrace repository. Cool. And yeah, so feel free to screenshot this or something. I already have these cloned. When you do clone the mltrace demo repository, you'll have to install requirements.txt. So, I mean, I've done that. I recommend doing it in like some Conda environment or some, and specify Python 3.9 or whatever you want. But I've done that. So I've cloned mltrace demo and I've run like a pip install -r requirements.txt. And then for the mltrace, like setting up the whole logging procedure, you clone that. You don't have to run export db server equals localhost. It'll just silence your warnings that you'll get because you never set your database server. And then once you do that, then all you need to do is docker compose build, which I've done, and then docker compose up. You can also run it with the D flag if you don't want to see things or any logs. But I'll do that because, cool. Yeah, nothing is broken. And then when you go to localhost 8080, you should see, well, yours will probably look like this. And obviously there's no logs. But yeah, if you can get all of that, great. Things have been set up. And I will move on just for the sake of time, and but feel free to just ask questions if things don't work. I would be very surprised if everything runs perfectly smoothly. This whole talk, PhD projects never run smoothly. So I'll jump a little bit into the task, kind of describing the task. And this is using a public data set out there, and it's a binary classification task. And what that means is we're going to predict whether a passenger in some taxi ride is going to give their driver a reasonable tip. And maybe this really highlights that I've polled my PhD student friends on what is a reasonable tip. So please don't get mad at me if this is too low or too high for your taste. But I've arbitrarily chosen 10% of the fare to be the reasonable tip. And how are we going to know how well we're doing? We're going to look at the F1 score, which is basically a combination of precision and recall. And obviously, as like a good ML engineer, we're going to be logging just more than the F1 score. And we're going to have alert fatigue if we decide to pick alerts on it. But we'll be measuring accuracy, precision, and recall. And for the sake of this tutorial, because the original data set is pretty large, like the New York City Taxi and Limousine Commission data set, it's pretty large to download just off the bat. I have subsampled the data randomly, and that's what we'll be using just in case people's internet is not like lightning fast. Mine definitely isn't. Finally, in order to kind of build this pipeline, we'll be using like pandas data frames to house the data, and we'll be using scikit-learn random forest classifier. That it's not the best model, I bet you, out there, but we're just going to use that for now. So let me jump into describing the pipeline a little bit more. So I have this little diagram here. I don't know if people can see. It's kind of small. Maybe I'll make it bigger. But we have one script main.py in, let's do that. We have the script main.py in the mltrace demo repository. This contains like functions that represent different components of the pipeline. And the components here that we have are pretty straightforward, standard. We've got a cleaning component that takes in the raw data and kind of cleans it by removing some like corrupt data or some outliers. It removes rows that had like $0 fare, stuff like that. The second component is a feature generation component, which generates features. The train test split component splits the features into train and test sets. And it's really important, right, since this is a time series task, that we split Though we split on time and not randomly. We then have a training component that trains and evaluates a model. And then we have an inference component that actually runs the models on the features. And that's kind of what we use to run the model over several periods of time. And you can see the red highlighted components here are components used in the training pipeline. And then the blue ones are components used in the inference pipeline. And two components are shared, right? The cleaning and the feature generation components are shared between the pipelines. And just to simplify things, everything is in main.py. All of these functions are in main.py. I won't like go into super great detail, but you can definitely look at whatever you want in there. For our training, what we're going to do is we're going to train the model on data from January 2020. And then we're going to quote unquote like simulate maybe a deployment. And what that means is we're just going to run inference on like week after week from February 1st to May 31st. And then we'll see some performance drop. So let's run the pipelines just as they are now, and they should work. We're going to see some performance drop. So first we download the data. So if I'm back here, I want to do download.sh. My Wi-Fi is going great. It's actually terrible. But I'll download. Hopefully. Okay, cool. And it should be in a data folder. Cool. Looks good to me. And then what we're going to do is we're going to train the model on January 2020. And fortunately, the way to do that is to run Python main.py. And then there's two different modes. There's training and there's inference. We'll run it in training mode. Training. And there's also like a date range that's taken as an optional argument, but it defaults to January 2020. So we will just use the default. As you can see, we are running training on January 2020. And this is a big subsample of the data, or sorry, this is a small subsample of the data, so it'll go pretty fast. We split it 80-20. I'm pretty sure 80-20. Yeah, it looks like it. Yeah, we split it 80-20 on time. And our train set had a score of 71% accuracy, and then test of 73%. F1 scores are reasonably similar. Precision, recall, all posted here. And then I also printed out the feature importances for the random forest. There's this congestion surcharge feature that seems to be pretty important. And then there's like various other, like, I don't know, passenger count, trip distance, pickup hour, differences between the drop off and the pickup location codes, whether the work hours is like whether the ride was taken during working hours, like 9 to 5 on weekdays, or it's like binary indicator. Okay, and maybe this is definitely probably not the best model out there, but it'll make do. So if you the contents of your directory, you should probably see some model.joblib, which exists. That's good. And the reason we get that is because at the end of the trained model, we have dumped our model to model.joblib. So cool. We've all done all of this, and then now we want to run inference. Remember that the inference pipeline kind of does cleaning, feature gen, and then inference. And how we're going to do that is I've written a separate script to run inference, and that's just so we can run this weekly inference in one command rather than do Python main.py mode equals inference like how many ever weeks. And if you want to check it out, basically all I do is take a start date, end date, and then I iterate through all the weeks in this range, and then I run Python main.py mode equals inference and the start and the end. So we'll do that. I can't see my own screen. Okay. Oh. Hmm. On. Inference. Okay. And we see, actually, I should have done a pretty print. My bad. That's we'll do next time. But see that the F1 score kind of starts out at 84%, 83%, 81, 82%, 83%, 82%, 83%, 79%, 73%, 71%, below 70, 68, 64, 63, 69, 70. And if we look at also, right, like precision, well, obviously precision and recall are going to go down because F1 went down. We can also look at accuracy, right, started out at 73, and then went down to kind of 59, 58, 60 towards the end. And like, yeah, obviously COVID happened, and like that's the big elephant in the room. The point is, yeah, we observe the performance degradation, and you all don't know what the code is in the pipeline because you didn't write it. But maybe you're tasked with debugging something like this. Maybe I say, hey, something is wrong. Well, first, the question is like, when did something wrong happen? When would I flag that something is wrong? Whenever we get to the 73 here or the 79 here, I don't know, take your pick. But then once you know something is wrong, then like a number of things could have been wrong. Like maybe I wrote the code incorrectly and there's like a bug in generating the features. Maybe I'm cleaning the data wrong. Maybe I name all your favorite sources of error, right? Because you don't know, you don't have any confidence over what I've written. And also, frankly, I probably don't have confidence over what I've written. And then the question then becomes like, what do we do? What do we do here now that we've seen the metrics drop over time? And if we were at a company, right, alarms would be going off. Somebody is debugging the pipeline. Most likely they have not built end-to-end what's going on. And where do we begin debugging? Another caveat I want to point out is in this example, we have the code and the data pretty centralized, right? Like truly one file is running the pipeline. But in practice, right, you have nothing is truly super centralized, right? You have different code bases, maybe with different repositories, maybe you have different data sources, maybe, right? It's not like a single path to an S3 bucket that houses all of your data. Maybe you have different data stores, like maybe you have like a Postgres table as well as like a Redis cache or so. I don't know, like truly imagine whatever you want. So that makes things even harder, but we'll constrain ourselves to a simple case here where everything is centralized. And what we're going to do is kind of integrate mltrace into our pipeline to kind of figure out what's going on. So what we're going to do is we're just going to add some code to get some tracing, and I'll show you that in a second. But the way we do that, as I hinted before, is we have some sort of component specifications that we define. So you can look at the screenshot on the left. So here's an example component spec. We subclass the component. We created like a cleaning component, for example, with all of its various metadata. So maybe it's a name's cleaning and we have some owner and whatnot. And once we define them, then we can instrument our pipelines by adding the cleaning run decorator to the function that we already have that represents the component. So on the right, imagine this is main.py. We import the components that we've defined in components.py, and then we can add the decorator. And this auto log parameter, all it does is it looks at the inputs and it auto logs any data frames or it auto-logs any like large files. I don't remember the threshold off the top of my head. It's in the documentation, I think. And then for outputs, it also auto-logs any like data frames that are created, any large data frames or models or whatnot that are created. And if you don't want to use autolog, you can also like manually specify the variables that you want to log as inputs and outputs, but we'll use autologs here. So what we'll do for our first exercise is we will instrument all the other functions with components. So I've defined components in components.py, which exist somewhere here, correct. And the exercise here is to just instrument main.py's functions with them. So we'll do the first one, we'll do cleaning. So here, what I want to do is, actually, did I import it? Yeah, I've imported it, cool. Run log equals true. Cool. I don't remember what it's called. Feature gen. Cool. And of course, right, like you don't need to create component specs. If you're gonna have simple components, you could probably like just create like a component. You could do like some sort of thing here, like component name equals blah, 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 like various metadata in there, .run. I just think it's easier to just actually directly specify what you want because it's more reusable. I think here we have train test split, yeah. That's just a helper function, train. Okay, and then finally, we have inference. That's not how you spell inference. Okay, I've done all of this. And what this will do is it will kind of trace data flow through the pipeline while I run it. But I need to rerun everything. So we've run it, and then let's verify when we're in the UI that some stuff has gotten logged. Cool, yes. So the latest component runs exist. Good stuff. And then lost my turn. Oh, we're gonna run inference. Cool. It's running. And things are getting populated to the database, as we can see, which is all good. But going back, okay, now we're starting to see our performance drop. And maybe you want to see kind of like what were the recent inference runs. So you can go history, inference, command list, preliminary command list is here. But yeah, okay, so here are all the recent inference runs that we had. We're working on kind of also logging metrics or integrations with MLflow to log metrics here. Right now we don't have that, so we have to make a very nice educated guess on what gibberish we want to click. I don't know, maybe let's try something like 5 steps ago. Who knows? So the inference card shows inputs and outputs, and then maybe I click an output. And then I can see kind of all of the steps that were involved in generating this prediction. And it looks really annoying and large. And if we recall correctly, that's because we have multiple dependencies, right? Inference depends on a model and data. The model comes out of training, which comes out of some train test split, which comes out of some feature generation, which comes out of some cleaning. And then, of course, the data that's actually being fed into the inference pipeline. And that's just like cleaned data that goes through feature generation that goes directly to inference. And so we can kind of look at these kind of logged versions of the data at that time to kind of see what's going on. And truly, unfortunately, we are still working on better ways to kind of quickly materialize the state for whatever researcher, or sorry, whatever practitioners want to look at it. But maybe first thing that I want to do is look at, I want to look at the features that came out of training and maybe compare them to my inference features. I don't know, as a first glance. So what I'll do is I'll create some sort of notebook. Might be getting ahead of myself. Oh yeah, I'm getting ahead of myself, but we saw this. For exercise 2, we want to figure out what's going on. So we have captured our intermediates. Why don't we load and analyze them? So I'll make a notebook. What do I want to name the notebook? Debug IPYB. And we're going to use VS Code notebook, which is a real hit or miss for me. So hopefully it works out. And let's select the correct thing, and let's verify I have the right environment going on. And then run this. No, I will not take your survey now. Okay, so it's running this good. And what we're going to do is load these intermediates. So the way that we want to do that is figure out what we want to load. So that's this feature, I believe. So, man, okay, I don't know why that, like, I'm not able to click on this and then see the, I think in the, I should have, maybe I didn't rebuild the latest version of the Docker container, I don't know. But I think for you guys, if you're clicking on this, if you've already built your containers, you should be able to click on this and it'll automatically copy it to your clipboard, but clearly it's not happening to me. Correct me if I'm wrong, and then I'll definitely go and debug that. But we'll do this terrible exercise of trying to figure out, so train features equals mltrace load. And we are going to have to load this whole thing, which again, all the joys of working at a very early stage project. Mltrace dot show code snapshot. That bug just shows you like the code that was used for that run of whatever component this is, so feature gen. Yeah. Mltrace, what? Feature gen, features df. NQKYJ. And then we have 2021, 11, 15. And then we have 134921. And hopefully this works. Otherwise, wow, that's magical. Okay. And we'll do the same for inference. GitHub Copilot, by the way. For this one, we want features df ahj QM 2021 1115 135023. Go figure. Oh no, yeah, features df ahj gm. Sorry, everyone had to go through that. But we can ahead these guys just to verify that they're kind of what we expect. So that's good, right? The train has dates in January 2020, and see what week we've got going on here. March something. And then we can kind of look at some of the stats we have going on. I believe. Okay, so that's the train features. And off the bat, we see some odd things, right? Like, for example, the size of the train features is 502,000. Just curious which IDE. I'm using VS Code, and I'm using VS Code notebooks. Or do they have the ability? Sorry, the ability to kind of view notebooks and run them in the IDE. Cool. So what was I saying? Oh yeah. So we have like what 500K plus train features, and we have 4,000 inference features. And even if we multiply 4,000 by 4, we will not get something close to 532,000. So that's something interesting. We can also look at other kinds of, I don't know, features going on. So maybe standard deviations, maybe pickup minute, kind of checks out. Trip time seems like a larger standard deviation. Interesting, but shorter. Trip speed, trip distance. I think here, right, something that we're location ID, recode ID, vendor ID. So all of these things, it seems like some of the standard deviations are larger, but maybe the means are somewhat similar. But I will spare everyone kind of the me typing out every week's of inference features. That definitely is something I need to fix. And you can imagine, right, like going through, I don't know, batches of inference features, looking at summary statistics or whatever, and kind of comparing them. So what we're going to do kind of is, I'll just skip and tell you that some of these batches that are fed into inference, right, because of COVID, there were fewer drives, there are more outliers. So some of the batches just have some pretty insane outliers. And maybe what we can do is look at batches of data and we can flag outliers somehow. Or we can like compute statistics and log them or show them to the user. And what we're going to do is use mltrace testing abstraction to encode this kind of computation that we want to perform at runtime. So I've written 3 tests here, just for simplicity's sake. Feel free to write your own. But the idea behind tests is they're just units of computation that can be executed before and after the components are run. And the 3 that I've kind of made for this tutorial are the outliers test, which prints some summary statistics. And tests for outliers is defined by z-score. Training assumptions test, which tests for train test leakage. and makes sure the data doesn't have a large class imbalance. So this test would fail, for example, if I randomly split my features into train test sets, because then you would have some sort of leakage or some sort of, maybe some sort of overlap. And then finally, we have a model integrity test, which checks that the model did not overfit, and the feature affordances aren't like heavily skewed towards one or two features. And I've made the mistake in the past of using like some aggregation of the label as a feature. So model integrity test would have caught that. And in order to do this, I don't know why I can't. Okay, yeah, in order to do this, you can kind of just take the test and insert it as a trigger into the component specification like we have here. Maybe I want to test for outliers after my features are generated. And what I can do is just set the after tests parameter of the feature gen component spec. And I'll go through kind of the tests again. So, sorry for the mishap in this whole notebook experience. It was supposed to be easier to load and compare them. But the tests here that we have, as I mentioned, are outliers, training assumptions, and model integrity. The way to write a test is very similar to like unit testing, Python. You write a class, call your test. You write some functions that represent your tests, and they must be prefixed with test, like you would imagine PyTest, or sorry, in unit test. And so some of the stuff that we have here is you don't actually have to put an assertion in these functions. The idea here is these functions just get executed in the before or after as you specify for a component. And the parameters that are specified in the spec here, or in the signature, they must exist somewhere in the function that this test is being applied to. So for example, test compute stats, this test compute stats takes in a df. If we use outliers test for feature gen, we just need to make sure that for our feature gen, we have some sort of df to use, which we do. Yeah, we have some sort of df to run here. You can think of it as like some sort of props situation, if you're familiar with that. Yeah, so we also have this test z-score function that pretty much just uses some sort of z-score thresholding to figure out whether there are a lot of outliers or not. These are just really arbitrary values, and then you can change them. You can pass them into the component specifications. Let's say I wanted to have a different standard deviation cutoff. I could pass like a standard dev cutoff equals something. Well, maybe not. Yeah, if I wanted to. But okay, moving on. So what we're gonna do for our next exercise is to incorporate these tests into the mltrace components. So we'll add the training assumptions test, the model integrity test, right? We already are adding the after test equals outlier test to feature gen. So yeah, we'll just add the other tests. So let's see, outliers test, main.py. We want to say after test equals something. Make sure I did incorporate. Oh, I probably need to do a import star. And then I also want to add the training assumptions test, which should be satisfied before you train your model. And maybe we can do that. I don't know. We can do that here. So after test equals assumptions test. And we just need to make sure that our parameters in training assumptions test function. So train df, test df, date column, label column should exist. Date column, label column, train df, test df. Perfect. They exist in here. All good. And then finally, the model integrity test. Well, that would probably come after you've made a model. So this equals model integrity test. And got going on here. Train scores, test scores, feature importances. So let's go back. Let's look. Train scores, test scores, feature importances. So all's good. We have everything defined as we need to. Then we can run the pipelines as we've done before. So let's do that. And while this is training, people have asked questions. Video recording and PowerPoint slides. I will definitely try to get my slides to everybody somehow, for sure. Okay, so I've trained it, and something new has been printed, which makes sense because we wanted to print out the in our outliers test, we had a test compute stats, which just printed out the data frame .describe going on. So this makes some sense. We are seeing kind of this high passive account, total amount. Okay, and then we rerun inference. And here, we're going to start seeing things. So 132,000 per week, 134,000 per week, 120,000 in that week, 133. All good stuff. 19,904, 104,000. Crazy. So 28,000. Something failed. We found some outlier values in that batch. Okay. Also found outlier values in this batch. Outlier values in this batch. Okay, so as you can see, right, like computation is being performed. What if you scale features with different methods? Example, you have only one threshold. Great question. This is why the interface here requires users to define their own tests, because you all will know how you're creating your features, and nobody else will know what are the tests to use. So you're totally right. If we're using z-score scaling, or if we assume our distributions of features are normally distributed, then maybe this is a good test. If they're very long-tailed or bimodal or some other distribution, this is an awful test to run. So a lot of this is kind of just trying to figure out what are the correct tests that you should be running for the problem at your hand, kind of like as you would write your own unit test. And of course, like some tests will be similar across different kinds of applications. Like maybe you're trying to do like image classification tests on those kinds of problems, or those kinds of pipelines might be similar. Whereas if you're trying to do like a time series pipeline, it makes sense to be running different kinds of tests based on the shape of your distribution. Good question. Okay, so going back to this, like clearly we're not catching all failures, and we're not going to catch all failures. I think a lot of the times, right, like there's no way you can like get full coverage, right, in just a handful of tests. And the other part is you may not ever be able to get full coverage due to the nature of machine learning, because you just don't really know how your data is going to change over time, and you don't know whether your model will always be relevant. So that's where kind of monitoring comes into play, something we're actively working on. I'll go back to this and maybe touch a little bit on some of the takeaways that we've got. I know it's pretty late, but But in this tutorial, what did we do? We trained a model, we simulate deployment, and then we kind of investigated the performance drop and added tests. Tests is a very loose word, but there's tons and tons of room for improvement. And I'll talk about that a little bit in our ongoing work. So one big thing that we don't do right now is right now the tests that you write, for example, here, can only look at kind of the data that's happening in that batch. But a lot of the times, right, you want to be able to compare historical batches of that same component. So what we want to do is figure out like what's a great way to materialize like historical component run inputs and outputs to use for users who are writing and running these tests. So maybe that's something like I have like a self dot history dot df, or dot df. And that's like an array of historical data frames that have been seen here in this function. And then maybe I just want the last one, and then I can compare it to this one. I don't know. I'm just imagining some interface like that. Totally actively working on it. If you have any thoughts or ideas, super appreciated. Also working on kind of logging parameters and showing visualizations, or just even basically showing this logs in the UI. Right now, they're kind of only printed here as standard out, but we'll try to get them back in our UI. And then finally, we are thinking about like what are different kinds of common ML pipelines or components that you would see spread across different applications, like robotics, for example, or language, for example, translate. And how can we kind of like, how can we do research to populate some sort of like library of off-the-shelf components? Or sorry, library of components that can be used to construct off-the-shelf pipelines. Question, currently the test violations appear in logs. Are there integrations to notify generic metric service? We are currently working on that for sure. One project we're working on is like an integration for Prometheus, and maybe that's not the route. Maybe we need to do integrations with all sorts of alert services, but definitely in the roadmap. And then history, what about a database approach, pass a DB reference that could be more flexible? When you say DB reference, like, what are you imagining? Like, feel free to dump that in the chat, and I'll get back to that question. Like I could imagine like the way that people kind of query the database here, database of logs, right? Like you could imagine like history, inference. What does that do? That like selects star with component run name equals inference, or sorry, component name equals inference, order by start time descending. Is that, I don't know. Yeah, okay, elaborate on that and then I can get back to the question. We're also working on distribution shift, and this is like really a loaded term, but specifically, what are we interested in? How do we know when to retrain our model? This is like the underlying question that all of us are dying to have the answer to, right? But unfortunately, it's very task dependent, context dependent, and resource dependent. And different people are approaching the problem in different ways. Maybe some CS theorists, some of my friends who are working on this, are saying, okay, well, it's impossible to know if your data has changed unless you define like super strong assumptions and you have like at best 3 features. And clearly that's not practical because people are using more than, I don't know, people are actually doing high dimensional data modeling. Something I'm pretty excited about doing next semester is to think about leveraging like approximate query processing techniques for doing distribution shift, for example, like binning histograms and being able to compute these kinds of like large scale metrics pretty efficiently. And then what did I do at my previous job? Well, what I did was I plotted df.hist and looked at that every single run and with my own eyeballs decided whether I needed to retrain my model. And clearly this is not the best technique. I would never wish that upon anyone, but I think this is actually pretty common when I talk to other people. So it's unfortunate, definitely an area that we need to actively work on. And maybe in a research context, that means we need better, and like when I say better, like dynamic data benchmarks. So we actually learn to model distribution shift or something like that. So if you are interested in kind of open sourcing like a time series data stream that you might have at your company or something, for tractable ML tasks to do research on, please email me. I would absolutely love to work with you. I think it's very hard to make progress on this from an academic setting if there's no like access to kind of time series data. And then finally, we are also always doing engineering because you got to do that. Efficient artifact and model versioning, right? It's easier to do it when you talk about versioning data, right? You just like store diffs of your data across successive pipeline runs. But versioning models is really annoying, right? Because let's say I fine tune my model one step further, all my parameters can change. So it's how do you like efficiently kind of checkpoint and version those? We're also working on kind of gRPC integration so we can support languages that are not just Python. We've done this, so I should remove asynchronous testing and logging. Anyways, all sorts of optimizations to make things run faster for bigger workloads and for larger teams. Yeah, and finally, last but not least, here are some resources that I realize are not super helpful because you don't have the slides. So when you do get the slides, hopefully these links will be useful. And of course, if you want to get involved, have any feedback on like, I'm especially interested in feedback on like designs of testing. Like I know people use assert statements all throughout their pipelines, and I personally did that before. Any feedback on kind of like the design to moving towards like writing your tests in a more reasonable fashion and using them as like triggers would be super helpful. Email me, first name, last name at Berkeley. And lastly, I need to thank my advisor, Aditya, and 2 undergrads that I work with, Aditi and Boyuan. Super awesome to work with. And yeah, always looking for more collaborations. Thanks, everyone. And I will go to questions.
Thank you so much, Shreya. That's great. And I hope that some folks here can reach out and hopefully collaborate. I think that's a really great opportunity.
Cool.
So yeah, if anybody has any questions, we'll give you a minute to shoot those in the chat.
I think there's one that I haven't gotten to. Any high-level thoughts on observability in an adversarial setting, fraud detection? Okay, so I think with, I don't know what adversarial setting means, but I will take this as like high stakes setting. So maybe that's like fraud detection, yeah, or credit card, or like loan approvals, or like mortgage generation, stuff like that. When talking to people, the main things I've noticed is you need to kind of store like logs, metrics and traces over really long periods of time, and maybe for also regulation purposes. So kind of like designing or kind of having the space to store all of that and not like purge everything that you're doing all the time is good. For fraud detection specifically, I think observability is challenging because you have such high class imbalance all the time. I also did like a pretty high class imbalance ML. One of the pipelines that I built at my previous company had a really high class imbalance. And something that we found there is we had like expected class imbalance. And whenever the class imbalance was not as expected for periods of time, then we thought something was going on fishy with, I don't know, the data stream. So that might also be helpful to test for that.
Shreya, what are your plans? Do you have a timeline on the PhD? Do you have a way in which you would like this project to go, or any timelines around this particular project or future ambitions for it?
Yeah. So as I mentioned, one big project is like thinking about distribution shift, but from the perspective of like computing distance metrics, like defined distance metrics at scale efficiently. So that's something I'm going to start working on next semester. And I think that will really help like the monitoring case at least. And the other thing is like being able to do that in-house and not like, I don't know, give away your data via some endpoint to some like monitoring provider would be pretty nice. The other thing that I'm pretty interested in, of course, is like the library of reusable components for specific tasks. I don't know. I think this is like easily a few years of research, so I can't comment on like after that.
Very interesting. Yeah. No, those are all great. Sheldon asked, any updates and changes to mltrace documented in the repository?
Yeah, I should do a better job. I will do a better job, but there's a change log in the documentation. So.
Thank you so much, Shreya. I think that's great. I mean, we've taken up a lot of your time. I really appreciate you being so generous. And thank you so much for giving us another great presentation. We have, thanks everyone for joining. We have an email that will go out with the magic link, which is a link for the hop-in and platform access. I believe that's going up tonight. However, one more day of workshops tomorrow. Videos for most of those sessions will be sent out once edited. So if anything that you've missed, you will receive an email with those links. And that's it for myself. Thank you so much, Shreya, and thank you everybody for joining. I really appreciate you taking the time, and I wish you all the best with your PhD and this project. Thanks for sharing.
Thank you. Yeah, thanks for having me, and thanks everyone for making it through this whole thing.
Take care. Thanks all.